Good morning, everyone. Welcome again to ITC conference. This is Sajidul. I am a PhD student at University of Florida, working with Dr. Mark Tehanipur. Today, I will be presenting on our regular paper titled LL-ATPG, Logic Locking Aware Test Using Valet Keys in an Untrusted Environment. Nowadays, ICs are built together with all the components fabricated in one single chip, which encouraged IPs from different companies to be integrated into one IC and introduced a new market for IP vendors. However, with many entities involved in design, manufacturing, integration, and distribution, which are located across the globe, original intellectual property owners can no longer monitor the entire process. As a result, they are now facing threats of IP piracy, IP theft, tampering, counterfeiting, reverse engineering, and IC overproduction. So one of the concepts to thwart the IP piracy is logic locking. In software development, obfuscation is the act of deliberately creating source codes that are developed difficult to understand. Though obfuscation has been heavily explored by researchers in software development, the concept is moderately newer in the hardware domain. The concept of locking and the use of locking gates in a design was first proposed at 2006 in IEEE VTS, which was used to lock the scan chain for scan-based security issues. The goal of logic locking is to hide original functionality and prevent reverse engineering and IP piracy. But it achieves this goal by inserting additional gates that are controlled by key inputs into the design. The proper functioning of the design is ensured by correct unlocking key. So, for example, for this circuit that is presented in the below of the slide, if the first equation represents the functionality of the original circuit, then after we insert K1 and K2 key gate, the equation will be changed to something like this, which is the O1 prime. The assumption is that the correct unlocking key will be applied from a tamper-proof memory, and only with the correct unlocking key, the functionality will be restored. The manufacturing test of logic locking can be done before activation of the chip with the secret chip unlocking key or after the activation. Both the process poses their own performance and security challenges in terms of testability, test coverage, and all the different test-related metrics. In case of pre-activation test, after the chip is fabricated, the testing is done before the activation takes place. So there might be a question like, so how the chip can be tested when it is not activated? So as we all know that manufacturing test is a structural test. It does not have anything to do with the functionality. So the actual functionality is not necessary to perform the manufacturing test. So with a set of dummy keys, the keys can be triggered with some inputs and the manufacturing test can be performed. In case of the post-activation test, a chip unlocking key is shared with the foundry and the test patterns are also generated with the chip unlocking key in place. So this portion conflicts with the original objective of the logic locking. However, in case of the pre-activation test, the chip unlocking key is not in place when the test patterns are generated and also when the manufacturing test is performed. So how these test patterns can be generated with the logic locking in place? That should be our next question. So let's have a look at how the test patterns can be generated in a logic locking. So in case of both the pre-activation test and the post-activation test, a constraint with either the chip unlocking key or the dummy key needs to be applied to the key inputs during the test pattern generation process. So applying a key constraint sets the corresponding key bit line into a specific bit value that we all understand. And the problem is this specific bit value resists the LTPG tool from detecting some of the faults that cannot be triggered with such a specific value. For example, in this tau example, we can see that we are trying to detect a stuck at fault at the output of K1. So let's say one of the input of the K1 key gate is X, and the other one is coming from the key input. So based on the value of the K1 and K2, we will be able to detect some of the faults, and we will not be able to detect some of the faults from our fault list. So obviously, we can see that this type of test pattern generation process suffers from compromised test coverage. Then let us have a look at what happens if we attempt to generate the test patterns without even applying any key constraints. So we can do that. In such case, ATPG tools will be treating the key inputs same as the primary inputs. So for example, if ATPG tool wants to detect a fault at the output of K2, then it will try to generate what are the input patterns it needs to apply to trigger this fault. So by which I mean, what should be the value of I4, I5, I6, and K2 to detect the fault at the output of K2 gate. So the similar way it treats the primary inputs, it will treat the key inputs in the same manner, and tool will try to generate the patterns to detect such faults. The problem is the tool will have complete flexibility in generating as much different key constraints it needs, and which will relate to a large number of key constraints and all those sort of things. And one of the last technique, the way test patterns can be generated is we can consider the key gates as part of the scan chain. So in such case, ATPG tool will have complete leverage to generate the necessary test patterns. However, this scheme also requires a large number of key constraints, and when we apply the key inputs to a set of key registers, then those registers are vulnerable to optical probing attacks and scan-based side channel attacks. Now, let us have a look at a motivating example. And this example will guide us to understand better about the LL-ATPG technique and why and it will also answer the question why we have chosen this approach. So let's say we apply a specific constraint and generate test patterns to detect the faults that are triggered by that specific key constraint. So if let's say we apply key value of 0 and 1 at the key gates of K1 and K2, and we apply a set of faults that are triggered by these specific key constraint. Then we generate the fault list that are not detected in the first round. So this part is very important. So at the end of the first round, the tool will generate which faults has not been detected in this round. In the next step, we will apply a different key constraint, and we will try to detect the faults that were not detected in the first round. So in the second round, we will not be trying to detect any previously detected faults. We will try to detect only the faults that are not detected in the previous iteration. So this way, we will keep moving until our test coverage is not met. And once our test coverage is met, we can accumulate all the different test patterns that have been generated in the previous iterations, and we can combine them and optimize them to get the ultimately higher test coverage. So once now we have discussed about the motivation, now let's have a look at what are the different goals and assumptions we have considered when we developed LL-ATPG. The goal of LL-ATPG is to find a suitable set of Valet keys that ensure adequate test coverage with minimal test cost overhead without sharing the secret unlocking key with the untrusted foundry or OSATs. So these Valet keys, they are just dummy keys. They will not activate the logic lock chip, and they have no relation with the secret unlocking key. So this part is very important because we will be generating the ATPG patterns with these value keys, and we will be performing the manufacturing test also with these value keys without going through the activation process. And we have a couple of assumptions when we develop the LL-ATPG. The first one is the class of logic locking. So in our work, we are considering function logic locking for evaluating the LL-ATPG method. However, LL-ATPG does not need that the underlying logic locking method must be functional. It can be either scan obfuscation. However, we need to keep in mind that scan obfuscation does not cover the functionality. So therefore, it has no impact on test coverage. We also want to emphasize that LL-ATPG is compatible with any kind of scan configuration. For example, let's say you have a scan compression, scan compaction, MBS, what sort of thing you name it, LL-ATPG will take care of it. And that is because based on the different scan configuration, there is a scan configuration file that needs to be generated during the synthesis process, and LL-ATPG loads that file during the test pattern generation process. We also want to mention that the type of logic locking is also agnostic in our case, by which we mean the LL-ATPG technique should be applicable to combinational, sequential, stack resistant scan obfuscation methods. And we also want to emphasize that the key injection process is actually, we consider that the keys should be value keys, which we also can term as dummy keys. And we can treat the key inputs as primary inputs, and we can apply the key constraint as with the value keys to generate the to perform the manufacturing test. So let's have a look into the overall flow of the LL-ATPG. So LL-ATPG is an iterative automated test pattern generation flow that keeps running until the target test coverage is met. So first of all, the gate level lock netlist needs to be loaded, and the simulation library needs to be imported in the tool. So so just to give you an information that the overall flow is developed in Synopsys Tetramax. However, the same algorithm can be loaded into any other test pattern generation method. So once the library has been loaded, the ATPG tool needs to build the model of the test generating design, and then a key constraint needs to be applied as a value key into the key inputs of the logic log netlist. After that, a design rule check needs to be performed based on the STL procedures. So once the DRC is passed, then a fault needs to be fault database needs to be created. So once the fault database is created, then LL-ATPG will try to detect all the faults from the database. However, we all understand that ATPG tool will not be able to detect like all of it. So let's say it detects like 90% of the fault. So once it generates the test coverage, then it will be checked with the target test coverage. So if the current test coverage is smaller than the target coverage, then LL-ATPG will report the patterns and the undetected fault. So for in this case, it will report the 10% faults that has not been detected in this iteration. So based on these faults, the tool will switch to a DRC mode, and it will remove the previous key constraint. And then it will try to apply a different key constraint as a value key into the key inputs. And with this new constraint, the same DRC check will be done, and then the fault database will be updated with the previously undetected fault. So this part is again very important, because in the second iteration, it will not try to detect all the faults again. It will only attempt to detect the previously undetected ones. So then the ATPG tool will be ran again to detect the previously undetected faults. And after the second iteration, the overall test coverage of the first and second iteration will be calculated, and the tool will check whether the combined test coverage is greater than the target. If it is greater than the target, then the tool will combine the overall test patterns from these two iterations and generate the test benches. If it is not meeting the target, then the flow will run again. It will apply a new set of constraints and try to achieve the ultimate test coverage. So how the test key constraints are generated in this algorithm. So as we have already mentioned that LL-ATPG applies value keys as key constraint, which are independent of the unlocking keys. So the constraint generation algorithm takes the number of key inputs and the log number from the LL-ATPG algorithm, and it applies the key constraint based on the basic test pattern generation method. For example, in the first iteration, it applies all 1. In the second iteration, it applies all 0. Then it changes the bits and flip the bits again. So this way, it keeps generating the key constraint. So at the fifth iteration, if the underlying logic locking method is a random logic locking method, then it keeps applying a random key constraint. Otherwise, it suggests to insert test points. So please note that we could have come up with an approach that could generate secret logic locking keys in a intelligent approach, but that would risk the leaking of the secret key through the generated test patterns. So let's have a look at a toy example. Here we are considering the GPS core of the CEP SoC, which has more than 230K gates and 10K flip-flops. When we have inserted a 1024-bit random key gates here, and we varied the test coverage and applied LL-ATPG. So we can see that with a target coverage of 99.5%, LL-ATPG was able to achieve that. And in the second step, we incremented the target coverage to 99.75%. And we can see that in the second target, it didn't try to detect all the faults. It tried to detect only the previously undetected faults. And it keeps generating the test coverage based on that. For example, in the third step, when we have shoot a target coverage of 99.95, it tried to encounter only the previously undetected faults. So that is the main effectiveness or main strength of this tool. Like, it never tries to detect the previous faults, only try to detect the current undetected faults. So if you have any question about the more results, and if you want to look into more results, please have a look into the paper, and mostly into the section 4. That would help to answer a lot of your questions regarding the results. And we also wanted to make sure that LL-ATPG does not reveal too much information to the foundry, which is the main purpose of all this work, right? So we want to emphasize that LL-ATPG is not an IC metering solution. It is just a test pattern generation algorithm for logic lock chips. So to make sure that it does not have any relation with the secret unlocking key or something like that, we attempted to perform the set attack on the logic lock chips based on the generated Valet keys. So how we did that? We tweaked the original SAT tool and developed a new one, which we call KeyNet SAT. In this SAT tool, we can plug in the key values and let the tool learn based on the key value. So we plug in the key constant or the Valet keys that are generated by LL-ATPG tool, and we perform the attack. So we can see that for different Valet keys, the bars are representing the attack time in terms of iteration and execution time for different Valet keys, and the red straight line represents the original result from the original set attack without applying any key constant. So we can see that in none of the case, LL-ATPG has more vulnerability than the underlying logic locking method. So we are nearly to the end of our conclusion, our presentation. So the main takeaway of this work is that LL-ATPG establishes a pre-activation test flow that ensures the manufacturing test of logic lock keys in the untrusted foundry without sharing the secret unlocking key. And based on our experimental results across a wide range of benchmark and logic locking methods, we can guarantee that LL-ATPG flow can achieve high test coverage, require less Valet keys, irrespective of the type of lock. And we also consider to expand our work for different area tools, different state-of-the-art logic locking methods. That is part of our future work. So that concludes my discussion today. If you have any question, we'll be happy to answer that. Thank you.